Hello everyone. My name's Toby, and welcome to my talk titled Tyre Rubber Particles, Prioritisation of Additives and Development of Environmental Exposure Scenarios. So just a little bit of housekeeping, and I won't dwell on it too long because that introduction was pretty thorough. I'm a specialist within the Chemicals Assessment Unit, and as Nick said, we support on UK REACH, CLP, POPs, and risk management options analysis. In regard to the Tyre projects I'm going to talk about today, Dr. John Cross is the project lead. Some of you might have met him last year. I'm the technical lead, and WSP and WCA have contributed to both projects as consultants. So I think it's pretty safe to say that we all use and interact with tyres probably on a daily basis, and I think most of us will have used tyres to get here today. I think just to support this and hammer it home, the European Tyre and Rubber Manufacturers Association estimate that 370 million car and truck tyres are sold in the EU in 2019, and the British Tyre Manufacturers Association estimate that 50 million tyres are sold in the UK every year. I wouldn't be here today, though, if there wasn't a downside to tyres, unfortunately. So aside from the issues with waste tyres and end-of-life tyres, there's been a lot of interest recently in tyre rubber particles, which are the particles released by abrasion of the tyre with the road surface. So it's estimated that about 2 kilogram or 12% of a standard car tyre is lost over the lifetime of that tyre. The composition of tyres is largely proprietary information, but there is an estimate that about 100 different chemicals are intentionally added during the manufacture of a tyre. Some of these may be hazardous to the environment. So one such additive is 6-ppd. I'm sure everyone's relatively familiar with it at this point. So this is an anti-ozonant that's used in tyres, which protects the tyre from attack by ozone over time. And over time, 6-ppd can migrate to the surface of the tyre, so that there's always a steady supply. I've got a photo here as well from the ITRC and the US Tyre Manufacturers Association. And you can see the difference in rubber with and without 6-ppd. I believe this was measured at elevated temperature and concentration of ozone, but it demonstrates nicely the difference. So when 6-ppd reacts with ozone, it can form 6-ppdq. In 2021, this was found to be responsible for a number of fish mortality events in North America, specifically for the coho salmon. There's been a lot of research on this since, and it's been linked to other salmonoids, fish mortality events since then. So we know that 6-ppd Q is hazardous for the environment, but what about other chemicals that may be present within tyres? So you can group chemicals into categories roughly based on their the reason that they're added to tyres. So briefly, you have structural chemicals such as rubbers and fillers, processing aids such as plasticizers, oils and waxes, vulcanizing agents to cross-link the polymer chains, and then you'll have protection additives that, such as anti-ozonants and antioxidants. So we know that particles have been released into the environment, and we know that a certain amount of chemical is contained within. What we don't know is how much Tyre rubber particles have been released into the environment, the specific composition of the chemicals, of the tyres and the chemicals within, the partitioning within the environment, and the leaching rate of the chemicals. And if you excuse my use of a stock graphic, it's a cocktail of unknowns. So to address this, the Environment Agency has commissioned 2 projects. The first is looking at exposure of Tyre rubber particles and leachate to the environment. And then the second is looking at the prioritisation of key chemicals. And then the aim of both of these projects is to determine what regulatory action, if any, is needed to address any chemicals of concern that are highlighted in these projects. So the first project is the exposure project. So this is looking at the releases of Tyre rubber particles and leachate into the environment. So this started with a literature review to determine the chemical concentrations and chemicals present within tyres. As I said earlier, it's largely proprietary information, but we have collected best estimates from the literature. And then likewise, we've also collected estimates of emission rates for different vehicles on different roads. The second part of this project was the development of a model. So the model considers local and regional scenarios, and it does so for 3 different road types. There's urban, rural, and motorways as the road categories. Each road category has its own specific parameters. So for example, we'd expect cleaning to occur on urban roads, and this is factored into the model, but it's not expected for motorways, for example. And I've got this graphic here, which is taken from the exposure report, that I think nicely shows the partitioning of particles within the environment and then the movement of leachate as well. So you can see that you've got the input of tyre mass on the left-hand side, which releases particles that are partitioned and intercepted in some cases, which go on to release leachate, which is also partitioned itself. Where it says input for environmental models, that's in reference to EUCs or other similar models. So the first scenario that the model can be used in is the local scenario. So you do this for a specific length of road. It'll be done across a shorter timescale, such as days. And in this scenario, we assume that the particles themselves are mobilized by rainfall, which will wash the particles off the road surface into the environment. So for the model to work its magic, the user has to input a few pieces of data. So we need vehicle frequency by vehicle type, which at least in the UK you can get from the Department of Transport website. We need the length of road and the type of road chosen between urban, rural, and motorway. And then we also need the number of days since rainfall above 2 millimeters occurred. So anything below 2 millimeters is assumed not to be strong enough to mobilize the particles from the road surface. And then there's a few parameters in the background of the model. So emission rate per vehicle type and the partitioning are set based on the literature search, but they can be updated by the end user if they need to. But it's not something you do every time you use the model. So I've just got a screenshot here of the model interface. So you can just see the different input parameters. At the top, you've got motorway, and then you've got the vehicle types and frequency, and then the length of road. And then there's a few road-specific parameters that you would also input for those roads. So to ground this in reality, we carried out a case study on a section of road, section of the A590, which is a road near Kendal in Cumbria in the UK. We picked this section of road because it's near the River Kent, which we know has got salmon and trout populations. And if we apply the data for this road to the model, we can estimate that about 470 kilogram of Tyre rubber particles are emitted to soil, and about 160 kilogram per year are emitted to water. So the other method of using the model is the regional scenario. So this is across a longer timescale, typically annually, and it does it for road networks. So we've currently got it set up for the whole of the Great British Strategic Road Network. It doesn't require any user input. All the parameters and data was collected during the literature search. So it just outputs the numbers, and it outputs particle tonnage by receiving compartment. Again, the end user can upgrade and update any data in the model as they see fit, but it's not something you do every time you use it. So just as an example, if we apply the regional scenario of the model to, for example, a car traveling down the motorway, we can estimate that 3% of Tyre rubber particles are released to air, about 57% are released to soil adjacent to the road, about 23% released to soil in the wider environment, and about 20% of Tyre rubber particles are released to watercourses. So as I said, the regional scenario can help, gives you Tyre rubber particle by receiving compartment, but you can also go a step before this, and it gives you the vehicle type per road type prior to partitioning and interception. So as a series of examples of what the model would output, we can estimate that 5,000 tons of Tyre rubber particles are released to watercourses annually, that 14,000 tons of Tyre rubber particles are intercepted annually by measures such as this drainage ditch. We can estimate that about 11,000 tons of Tyre rubber particles are released by cars on rural roads. This is prior to interception and partitioning. And likewise, we can estimate that about 9,000 tons of Tyre rubber particles are released by lorries on motorways, again, prior to partitioning and interception. And then just overall, as a bit of a headline figure, we can estimate that 53,000 tons of Tyre rubber particles are released annually across all vehicle types and road types. So, as I said earlier, there's the estimate that about 100 chemicals are added during tyre manufacture. While carrying out the exposure project, we identified 97 common substances that may be present within tyres. So these are those that are intentionally added and those that might be there as a result of degradation. The model is then able to estimate leaching from the rubber particles, and then based on the chemical properties of the specific chemical, it can estimate partitioning within the environment. So I threw together a really quick Sankey diagram, just for reference. The bars aren't to any scale, but I think it just demonstrates the movement of the different particles and leachate nicely. So you'll have tyre input mass, which releases a mass of particles. Some of this is removed by interception. The remainder goes on to undergo leaching, and then this leachate will then be spread to watercourses, soils, and some of it itself will be intercepted by wastewater treatment works, for example. So if we come back to our case study from earlier, we can estimate that about 32 grams of 6 ppd are released to watercourses annually as a result of this 1 kilometre stretch of road. About 115 grams of 6 ppd are released to agricultural soil annually, and 170 grams are released to the verges, the soil on the verges of the road annually. So, due to the availability of data and a number of assumptions, due to the availability of data, there's a number of limitations with the model, and then we've had to make a number of assumptions to ensure the data works together and facilitate the data usage. So, without dwelling too long on each one, we know that tyre age impacts wear rate. Newer tyres wear at a faster rate than older tyres, but we don't consider this within the model. We know that driving style, frequent braking, acceleration, and turning increases wear rate, but we don't directly consider this in the model. The road type categories that we've used of rural, urban, and motorway may lead to a bit of uncertainty for other road types. Electric cars, we know that they're heavier and they have greater torque than combustion cars. But what we don't have is a comparison of mass between combustion and electric, and we don't actually know how many electric cars are currently on Great British roads. We know that temperature has an effect on wear rate and to a lesser degree leaching rate, but we don't consider this in the model. Similar to particle size distribution and the impact of that on leaching rate, we don't consider that within the model. And I'll just come back to vehicle mass. We don't consider vehicle mass within the different classes of vehicles. So, for example, a passenger car with 4 people in will have slightly higher wear rate than one with 1 person in, but we've got no way of knowing this, so we don't consider it within the model. So the second project is the risk profiling and prioritization project. So we know that particles are being released, and we know that they are eventually releasing chemicals to the environment. What we need to do is prioritize any released chemicals based on hazard, so that we can take regulatory action if a risk is determined to be present. So to do this, we developed a ranking system based on hazard, tonnage, regulatory status, and concentration. With hazard, specifically PBT status, and tonnage scoring the most out of 15. We considered acute and chronic hazards, but we didn't consider impacts on human health, apart from when this contributed to the PBT status, because this is for other regulatory bodies to assess. And then we know that it might be an issue for terrestrial species, but we didn't consider this due to lack of data. So we took the 97 common substances identified within the exposure project, and then we narrowed it down to 63 chemicals based on stakeholder consultation and regulatory documents. And then we ranked these using the ranking system, which left us with 18 that were deemed to be of concern for this initial prioritization. So just as an example, I've got the top 3 from this initial shortlist. There's 4-tertiary-octylphenol, which is antioxidant within tyres, zinc oxide, which is a cross-link activator within tyres, and dibutyl phthalate, which is a plasticide within tyres. And they're all here because of their relatively high tonnage. 2 of them are endocrine disrupting, and all 3 of them are toxic to aquatic life. For reference, I've included 6-ppd. It's reassuring it's in this initial shortlist. Surprised it's not higher, and it's probably due to its potential PBT status and potential endocrine disrupting status. So we then took the 18 chemicals from the initial shortlist and ran them through the model from the exposure project. So this was done using the 53,000 tons of Tyre particles, and due to lack of data, we had to use the concentration of the chemical class as a placeholder for concentration of chemical. So just as an example, we know that antioxidants are anti-ozonants are present at around 2% of mass within a tyre. So we modelled 6-ppd as being present at 2%. So this output a leaching mass, which was then input into EUCs for regional modelling using EUC's defaults. This resulted in a PEC. The PEC was then compared to a PNEC, which was derived from regulatory documents, or to EQS values and regulatory thresholds if they existed. And from there, we had an RCR value. I've got here the top 10 chemicals from that ranking based on RCR values. All of them had an RCR above 1, which is indicating that there's a risk from their use in tyres. This is based on the calculation method and assumptions that we've used, and we know it needs further refinement, such as concentration as an input parameter. So we're aiming to finish both projects by April, after which they'll go for stakeholder consultation and hopefully be published on the Environment Agency website. Because they're not finished, I can't say with any certainty what the outcomes will be, and the decisions for someone way above my head as well, so I won't be making it. But I can give some examples of what the options and next steps might be. So first, under UK, we could carry out a risk management options analysis, which might propose authorization or restriction under UK REACH. It might also propose further research. Alternatively, apart from under UK REACH, there's mandatory classification and labelling, So, for example, 6-ppd is currently undergoing is being assessed under the CLP regulation, and as part of this, the data for 6-ppdq is being considered. And then there are a number of other options, such as further monitoring, substance evaluation, further modelling, or physical strategies such as settlement ponds, for example. And then finally, just before I finish, I'd just like to thank the European Tyre and Rubber Manufacturers Association, the British Tyre Manufacturers Association, Emission Analytics, US EPA, Department of Transport, and the Environment Agency Austria for their comments on the exposure report. Thank you for having us in the talk as well, Nick, and Emission Analytics. And yeah, thank you for your attention and time.
Thanks very much indeed. Packed with lots of interesting information. Who would like to ask a question to Tobias? Please.
Yeah. Thank you for your interesting talk. So my experience is, so if you, I meet several people. They showed me, they said to me, okay, show me the recipe, and then I say what is the reason for something, but this is not really true, because in rubber compounding you have a lot of reactions which are running, and that means you put something in, but when you destroy the tire, you will not find this materials back. You find something else, And I want to also make you aware that that there is a certain risk. If you maybe fix in one position something, you might generate a situation which is even more problematic. What I'm talking about here is the capability of microorganisms to degrade maybe something like these particles. I'm not really sure if all the tire wear is really in form of particles. Some of the tire wear will be a smeary film, very thin, you cannot see it, and this will be degraded by ozone and the sun and things like that. So you can conclude from the appearance of particles something in this direction, because in wintertime you have more dirt on the roads, in summertime it's gone, even if there is more abrasion, things like that. So that is, I want to only to say that is a quite complex material you are dealing with. Thank you.
Do you want to come back on that, or?
No, I think it's just something to think about, and it might be worth catching up after this to discuss.
Great. Well, we've also got a discussion panel as well after the next presentation. Yes, behind.
Hi, thanks for the talk. It was really interesting. You said there were about 100 chemicals that were leachable. Under what conditions were those leachable? Was that lab work or was that natural conditions?
Oh, sorry, the 100 chemicals, I can't quite remember where the number's from, but it's an estimation of intentionally added chemicals during manufacture. And then we also had the 97 common chemicals that we identified, which is a mix of degradation products and intentionally added chemicals. In terms of leaching, we don't consider the source, if that makes sense. I think every chemical is assumed to be available for leaching that is present within the tire. Does that answer this? Yeah, okay, cool.
Excellent. Thank you. And thanks again.
Brilliant. No, thank you.